So here's where we left off today with that integration by parts, the tabular method. And here's a quick run through of that same thing that we finished earlier today. We have to pick a u and a dv, and a limit is where it's at. So we decided to go with, for our, if we have to choose between t to the fourth and a polynomial, an x e to the 2t, which is an exponential function, we're going to choose polynomial to be u. And if we derive that u term out until it goes to 0, and we integrate the dv, e to the 2t, then we'll get down to until they're parallel to each other. So here are all the derivatives until we get to 0 with that polynomial, and that's kind of how it goes when you use a polynomial. And then when you do the antiderivative of 1/2 e to the 2t repeatedly, remember the antiderivative of e to the 2t is 1/2 e to the 2t. So there you have the antiderivatives of each of those respectively. And then let the table take over. And this is the fun part. Remember, the product of the diagonals, you start with the first diagonal, and it's positive, and then you follow it with a negative sign, and then the next diagonal is, don't worry about the sign, you just take the negative that you just tacked on there. Now you just do 4t cubed times 1/4 e to the 2t, that product. The 4 and the 1/4 cancel, so it's just t cubed e to the 2t. And then you tack on the plus sign after that, and you do your next diagonal product. We're going to tack on a minus sign after that one. Next diagonal product, tack on a plus sign after that, and next diagonal product. And if you want to, we were talking today at the end, maybe we should tack on a minus c instead of a plus c, just to keep with the table, but it doesn't matter. So this is it. This is your antiderivative for the integral you see above in example 10. A classic, great use of the tabular method when you have some polynomial with a higher degree. You definitely want to go with that. Now, example number 11, this changes things up a little bit. We're going to take, and if we follow the limit command, log of x is going to be our u. And so, logs go first, there's our u. That means x cubed is our dv, and if we run through this, it doesn't terminate. You can take the derivative of 1/x, the antiderivative of x cubed, and we can keep going. Both of those continue indefinitely. And so where do you stop? How do you know when to stop? I can just keep going. Antiderivative, derivative, antiderivative. Okay, so the derivative of log of x is 1/x. You make the x to the -1, and when you take the derivative of that, it becomes negative x to the -2, which is -1/x squared, which is the same as negative x to the -2. If you derive that, that's negative times a -2, which is a positive 2x to the -3. So we have 2/x cubed, and we just go on and on and on. The antiderivative, of course, those are pretty nice polynomials. And then the idea is, how do you know when to stop? Well, you can always stop anywhere. So let's just do a couple of these. Let's just run out a few diagonal products. All right, there's one diagonal product. Of course, we get to figure out our sign afterward. Let's put our plus and minuses. We'll tack a minus on. Next diagonal product. Next diagonal product. We could keep going, but there's something better. Let me back up on that again. So I'm going to go one more step back. This piece right here, at this juncture, we could keep going, or you can terminate wherever you like. We just did the first diagonal product. If you want to terminate, you just go to the last, like the end point of your diagonal, so that 1/4 x to the 4th. That row there, the place that we truncate, right there, that last place, that last part of the diagonal, that 1/4 x to the 4th, indicates the row where we stop. And then we end the antiderivative here is, or the derivative by parts, antiderivative by parts, is you do an integral of the product of those, that 1/x times 1/4 x to the 4th. If you did this longhand, this would be your result of doing uv minus the integral of v du. And if you want to go in there and write those, it might be helpful. I'm going to put it in there and see if I can put it in a particular color that stands out. What do you think, Waukee purple? I'm going to do it. So what we can put in there is, remember, this is the antiderivative, or we derived u, so this is actually du right here. That 1/x is our du. And then remember, we took the antiderivative dv, so this is v. Okay, so this is our v du, that row there. So if you think about it, here's u, v, minus the integral of v du. We have that, and we just stopped. But you can stop anywhere once you get to the end of a diagonal. If you just take the product of that row and integrate it, that's a good place to stop. So we can stop right there, and we can look at saying, all right, how am I going to evaluate that last integral there, that 1 over x, 1/4 x to the 4th? And you're probably seeing it already. You're probably seeing that, yeah, I could probably get rid of, probably do some simplification on that. So let's try it. Let's move forward a little bit. We copy that. All right, let's do the 1/4 out front. 1 over x and x to the 4th, make x cubed. Totally a doable integral. So the idea is you stop when you see that the product of a particular row is something you can integrate. If you can simplify the product of those and make it something it's integrable, you can stop there. So you could go further and stop, but the earlier you stop, the less work you have. So this totally works. So we could check it out. X cubed, integral of x cubed. Let's knock that out. Let's rewrite a little bit. All right, 1/16 x to the 4th. Great, we're done. Plus c at the end, and we're home free. That's the idea. When you stop if it continues forever at a place where you have an integrable product. And that means earlier is better than later, but we could have kept going. But it's nice to stop here, and we'll work with that. All right, so let's roll with this. The next part of this is we have to actually find the integral. So the question here is, and I didn't specify this up front, we had integral, when it says solve a differential equation, solve a differential equation means find z. Well, taking the antiderivative of this derivative means we're going to get z. That's the fundamental theorem speaking there. You take the integral of a derivative, you're going to get just that function z. We've done that, we got the antiderivative, but we need to do the specific antiderivative for a given point, which is the point when z equals 5 and x equals 1. So we're going to do a little substitution, which I've indicated here. If you put 1 in for x, log of 1, thankfully, is 0, so that's pretty simple. And then minus 1/16 times 1 to the 4th, we got, looks like we can solve for c, I'm thinking 5 and 1/16. And if we just make that into an improper fraction, 81/16. So ultimately, then we have to turn it into, here's our result. Here's the whole antiderivative with our brand new plus c, and we're home free. That's the specific solution to that differential equation through the given point. Okay, on to example number 12. Ready for this? Okay, so there is an average value problem. Strange, but it's you can actually, again, we're talking about integrating something that's a product of two functions. Perfect place for integration by parts. And that's what we're setting the stage for, is we have enough techniques to really tackle a lot of cool context problems, and now integrals are not going to be a hiccup along the way. We're just building that skill base so that we can do cooler stuff along the way. So the average value, if you remember, is an integral of a particular interval divided by the difference between the endpoints. So remember it as 1 over b minus a times the integral from a to b of a particular function will be its average value. So here we are, 0 to pi over 2. Here's our function, and then we want to divide it by the difference between our upper bound and lower bound, that b minus a piece. So let's work through that. Dividing by pi over 2 is the same as multiplying by 2 over pi. So there you go. There's going to be our average value. Totally doable in the calculator. In fact, we're going to just check our result from the TI calculator. I evaluate this at the end just to see if our worked out stuff works out. And it does, but it's pretty lengthy, so hang with me. Let's do our integration by parts, tabular method, because we got some repeated polynomial integration, and we need to simplify this. So here we are. Pick a u, polynomials before trig functions, so x cubed, then cosine 2x. Let's roll out the derivatives till we get to 0, and then anti-differentiate carefully. And don't forget the antiderivative of cosine of 2x. You have that 1/2 compensation, sine of 2x, out front. Okay, with all those pieces in place, we can just go ahead and check out our diagonal products. Alright, first we get that 2 over pi. And we take our first diagonal product, 1/2 x cubed sine of 2x. Got to throw in those signs so we can do the plus or minuses. So we're going to follow it with a minus. Next diagonal product, follow it with a plus. Next diagonal product, follow it with a minus. So if you need to pause and go back to these, just let me know. Next diagonal product, and follow that one with a plus. Well, we've hit the end of the road, so that'd be plus c if we're doing an indefinite integral, but this one's a definite integral from 0 to 2 pi. So that's evaluated. Now here's the fun part. If you put in pi over 2, in for any of those sine functions that you see there, sine of 2x. When you double it, sine of pi over 2 doubled is sine of pi. We know that's 0. So we get 0 for those two values for sure. But when we put pi over 2 in for the cosine of 2x, we're doing the cosine of pi, which is negative 1. So with those accounted for, we're going to have 3/4 pi over 2 squared. There's that negative 1 for cosine of 2 of pi over 2. And then at the end, negative 3/8 cosine of 2 pi over 2 ends up being cosine of pi, which is negative 1. So those are the evaluations for pi over 2. And then we put in 0 for x in there. Well, all the x terms, anything with an x is a part of the product, is going to cancel. So we're looking at negative 3/8 cosine of 2 times 0. Cosine of 0 is 1. So we're doing negative 3/8 times 1. So it's just negative 3/8. And then if we simplify that just ever so slightly more, pull some things together, we get the 2 over pi. And let's see, pi squared, we get a 4 times 4, 16, a couple of 3/8, makes a 6/8. It's about 0.7006. And if you integrate this, math 9, that one, finite, as we call it, same exact result. So that'd be our average value, the average height on that particular interval on that function. That's the end of that example. To the end, example 13. Here it is. Now, Kieran's supposed to be in bed. Say hi, Kieran. Okay, we'll send him to bed. Alright, e to the x cosine of x dx. Did you see that coming? Did you realize this? If you have secant in the bottom and the denominator, it's the same as cosine on top. If you didn't, there you go. There's your indication. There's, if you're deciding exponential versus trig function, which one gets u? It's Lippitt, has e before t. So there's u is e to the x. And look at that derivative. Derivative is e to the x, e to the x. Would have been the same if I had chosen e to the x to be v. So the interesting thing about this one is, if you swap these two, you get almost the same results. Very little variation, just a couple changes of sign. So ultimately, it actually doesn't matter what you choose for u and dv. Some might say it's easier to take the derivatives of cosine, sine, etc. than it is to do antiderivatives, so you might swap these. And that's fair if you want to do that. If it doesn't matter which one is which, then it might be better to think, well, I'd rather take derivatives of cosine, sine, etc. But I'm going to roll with it this way, just follow Lippitt and stick to it. This is the question. When do I stop? Look at that. It goes on and on forever. I could just do diagonal products ad nauseum, keep doing them. But the place we stop in this situation actually is when you get to a repeat of the integral that you're taking in the beginning. So here it is, e to the x and negative cosine of x. I know it's a different sign, but it's the same. Just pull out the negative, it's the same integral. The reason that's important, watch how this sets up. Alright, there's the integral of e to the x cosine of x dx. Keep your eye on that. Let's go ahead and do our diagonal products. There's the first one, and we follow it by a negative. Next diagonal product has that negative, but we're subtracting a negative. Okay, and then that's where we're supposed to stop. Well, and to truncate, what you do is just put in one more integral of, and we're going to follow, so this plus sign afterward is ever so important. See that plus sign there? We're still going to follow that diagonal product with a plus sign, but what we put on the end is when you're truncating, when you're stopping, you stop with the integral of the row you stopped in. So we're doing the integral of e to the x, negative cosine of x. There it is. So once I picked out where I wanted to stop, I do diagonal products till I reach that particular row, use the final plus sign there, and then you have the integral of that product in that particular row. So here it is. Now, this part, this is the fun part. Can you see this? Like terms, check that out. We've got like terms in our integrals. So actually what we can do is, that's on the right you have a negative e to the x cosine of x integral. So if I add that to the other side, check out what you get. You get 2 e to the x cosine of x equal to what's on the right hand side, that e to the x sine x plus cosine of x. We factor out the e to the x, and then we divide both sides by 2. And there you have it. That's our antiderivative for the original function we started with. That's slick. So that's the other time you know when to stop and truncate. The previous problem we stopped when we had a doable product in a row, a doable integral for the product of that row. This one we're stopping when we have a multiple of the original integral we started with, in this case the opposite sign, because we got that, as we solved, we got the like terms together, we had 2 of that original integral. We were able to divide both sides by 2, and voila, there you have it. So some pretty neat techniques for anti-differentiation integration by parts using the tabular method. So hopefully that gets you started. Now there's of course practice for this, in addition to all those integrals that you've been taking on over the last few days, or maybe just last night. There are more of these you got to practice, and then that means there's a test on our horizon, minus one more technique we got to throw into your tool chest. We're almost ready to wrap this up. Enjoy. See you guys soon.